Hi everyone, this is Ramalinga Prasad Kuppa. Welcome to my channel, Pharma World. Today's topic is interpretation of chromatograms as per USP 621 chapter. Interpretation of chromatograms is most critical part of chapter 621 of USP. In this video, let us understand some of the typical parameters and their intent in getting reliable results in HPLC analysis. What is a chromatogram? It is a quantitative response as a peak for the concentration of the compound. The response is as a two-dimensional peak-shaped curve with a specific height and area depending upon the concentration of the component peak. The response is quantitative. Lower the concentration, lower the area. Higher the concentration, higher the area. It is a bell-shaped curve starting at the baseline, gradually increases to maximum possible height and returns to baseline. When the separated component enters the detector, the baseline slowly starts rising and reaches a maximum height depending upon the concentration. Then it slowly and gradually drops down as the concentration decreases and reaches baseline again. The size and shape depends on the type of compound and type of analytical technique. Depending upon the analytical technique, the column, flow rate, the peak size may vary. Some peaks will be sharp and some will be broader. Depending upon the stationary phase and mobile phase, the peak elution pattern changes. Non-polar components elute faster in polar adsorbents. Main components of a chromatographic peak are height of the peak or the area of the peak and time of elution from the point of injection. These three parameters, area of the peak or height of the peak and time of elution, which is also called as retention time, are important for interpretation. Let us see basic parameters. Retention time. It is time elapsed from injection to detection of the compound. This is measured in minutes. Retention time increases with decreased flow rate of mobile phase, longer length of the column. Peak retention time increases as the flow of mobile phase decreases. The mobile phase separates the components slowly and hence it takes more time for elution. Retention time decreases with increased flow rate of mobile phase, smaller length of the column, increased oven temperature. Obviously, if the mobile phase flow rate is more, it pushes the components faster and hence elutes faster. Relative retention time RRT. It is the ratio of retention time with respect to retention time of a selected peak, mostly the main component peak. You must note that the relative retention time is only a numerical value and there is no unit of measure because it is the ratio of time of the component and the time of selected peak. Mostly it will be the API peak. Retention times are dependent on the above factors explained, whereas the RRT is constant. Also, it is easy to remember that if the value of RRT is lesser than 1, the peaks will elute before the main peak, and if it is more than 1, the peaks appear after the main peak. Resolution R. It is a measure of column efficiency to separate each component of the compound. Retention, selectivity, and efficiency are the main three factors that could affect the resolution. More the interaction with stationary phase, better the resolution. Selectivity depends on the capacity factor of the column. Selectivity is ratio of the two peaks for which resolution is required. More the factor, better the resolution. Efficiency is the measure of column capacity for getting sharper peaks. Sharper the peak, better the separation. Easier way to remember the formula is resolution is time difference between two adjacent peaks divided by the average of peak width of both the peaks. Resolution is calculated as 2 times the ratio of difference in two peaks divided by the sum of width of each peak. 2 multiplied by T2 minus T1 divided by W2 plus W1. This is important factor for accurate integration of peaks. Resolution is a measure of adequate separation of individual peak for integration. The resolution factor can be calculated as per the formula given here. If you assume the peak as a perfect Gaussian curve, plus or minus 2 sigma will have an overlap of 4.6% for two peaks. Normal distributed Gaussian curve will have 95.4% of the distribution. That means 2.3% of each peak is merged with each other. This is equivalent to a resolution factor of 1. The formula will be 1 multiplied by 4 sigma, 2 sigma on either side of the mean. If it is plus or minus 3 sigma, you will have 99.7% with 0.3% peak merger. That means 0.15% for each peak. If the value of resolution is 1.5, it ends up to 1.5 into 4, that's equal to 6. This calculation holds good, but still there is an overlap of 0.15% per peak. If you have a plus or minus 4 sigma, the resolution is more than 99.99%. This can be achieved by a resolution of 2. The equation will be 2 multiplied by 4, that is equal to 8, 4 sigma on either side of the curve. So it is a good resolution if it is more than 2. If the resolution is more than 2, it means it is a 100% separated peak. Try to understand the characteristics of the Gaussian curve for a normal distributed bell-shaped curve. Tailing factor, it is a measure of asymmetry of the peak. What is a symmetric structure? Left hand side and right hand side are equal, exactly half. So a symmetric peak will have exact 2 half from the mean on either side of the peak. When the two sides are not same, it is called asymmetric peak. That means one side is longer than the other. If the peak ascending side of the peak is longer than the descending side, it is called a fronting peak. If the descending side peak is longer, it is called a tailing. Of course, both are tails only. Tail is calculated as tailing factor with the formula W 0.05 divided by 2f. Tailing factor is also called symmetry factor. In the formula, W 0.05 is the width of the peak at 0.05% of the peak height. F is the half width of the peak calculated from the perpendicular line drawn at the mean line. So if 2f and W 0.05 are same, you get a tailing factor of 1. Generally, if the tailing factor is between 0.9 and 1.2, it is considered okay. At 0.9, there may be a slight fronting, whereas at 1.2, the tail may be slightly away from the half width. Depending upon the peak separation, sometimes tailing factor up to 2 is also okay. Theoretical plates. This is a state where the analyte will have equilibrium between mobile phase and stationary phase. Theoretical plates are not physically present to count. For easy understanding, it can be stated that a theoretical plate represents the distance that is required for every adsorption and desorption step. The movement of the analyte is assumed to be from one plate to the other as a series of equilibrated mobile phase plugs. At each plate, there is equilibrium between stationary phase and mobile phase for analyte. So, the greater the number of such plates, the more efficient is the separation power of the column. It is calculated as 16 multiplied by square of the ratio of time and width. There is another calculation which the software provides. It is 5.54 multiplied by the square of ratio of time and width at half height. Response factor. It is the ratio of peak area and concentration. To understand easily of RF, the response factor, it is the area per unit concentration in mg per ml. So total area divided by the concentration, you get area per unit concentration. Relative response factor is calculated as ratio of response of impurity and response of the reference impurity or API. Relative response factor is a ratio of two responses of analytes. This is called as RRF. This is important for calculating impurities, comparing the responses of the impurity with the reference standard of another impurity or API. RRF is calculated this way. This factor is relative to each other. Relative response factor is also calculated by slope method. Slope method is simple. For example, if you have data as xy, x1, y1, x2, y2, etc., slope can be calculated manually as y1 minus y divided by x1 minus x for the first set. The same calculation is done for any number of sets. However, your Excel sheet will help you. Prepare 5 or 6 replicate concentrations and inject individually to get the areas for each concentration. Jot down all the data in the Excel sheet. Go to spacebar, type equal to symbol, then type slope. Take the areas data in y-axis and concentration in x-axis. You get the slope. Do a similar activity for standard with which the RRF will be calculated. Slope of the impurity divided by the slope of reference standard will give you RRF. It is that simple. However, your Empower or any other software would give this data instantly. The explanation on RRF is only for knowledge. You can try just for fun once. Impurities are calculated as given below. Test area divided by standard area multiplied by standard dilution divided by test dilution, again multiplied by 1 by RRF multiplied by potency by 100, further multiplied by 100. But care should be taken to calculate the RRF accurately to reflect actual response of the impurity used. Peak to valley ratio is recommended when the two peaks are not separated fully. This happens mostly on shoulder peaks of the main peak. Before the impurity peak comes to baseline, the main peak starts from the valley. See the picture from USP chapter 621 for understanding. This is the height of the peak from baseline. This is the height of the valley from baseline. And the peak to valley ratio is HP by HV. Peak to valley ratio should be more than 1.5 at least. Signal to noise ratio is another important parameter. Noise is unavoidable. Some amount of noise will be always there. The signal to noise ratio is an estimate on how much the signal above the noise level can be detected. See this picture from USP chapter 621 for your understanding. This is the peak height. This is the noise height. Signal to noise ratio is calculated as 2h by h. This is derived like this. In fact, the signal to noise ratio is signal height divided by the noise height. But if you see, the noise is divided into two halves from the central line. So the calculation will be like this: h divided by half h, that is equal to 2h by small h. See the typical chromatogram. This is called the retention time for peak 1 and peak 2. This is the peak width for peak 1 and peak 2. This is peak width at half height. This is the peak height. Let us see what is system suitability. System suitability establishes the expected working conditions of the equipment train to get reproducible and accurate results. It is simple to understand. If all the parts of the equipment train work as expected, it is considered as system suitability for getting good results. Here, equipment train means the mobile phase, delivery system, injector, detector, and most importantly, the column. Most of the parameters discussed in earlier slides are part of system suitability. These tests are designed based on the concept that the equipment, electronics, analytical operations constitute an integral part of the system. Replicate injections of standard solutions are injected to establish consistency. Suitability of the data generated from replicate injections is evaluated for precision using statistical tools. Unless otherwise specified in the individual monograph, data from 5 replicate injections should have less than 2% RSD and more than 2% RST if the data is from 6 replicate injections. USP 621 says, for assay in drug substance monograph, where the value is 100% for the pure substance and no maximum RSD is stated, the maximum permitted percent RSD is calculated for a series of injections of the reference solution as percent RSD is equal to Kb root n by T90% n minus 1. This is interesting calculation. The percent RSD requirement for number of injections are given in the table 1 of the chapter. Try to understand the RSD calculations. If you are not able to understand easily, I will try to explain in another video. But give me feedback on this calculation. Adjustments to the operating parameters may be made if necessary in order to meet the system suitability requirements. Adjustments should not be made to compensate column failure or system malfunctioning. There are limitations for adjustments also. USP 621 describes several such parameters that may be adjusted. pH of mobile phase, concentration of salts of buffer, ratio of components in mobile phase are listed in adjustments. These are listed items for possible adjustments: stationary phase loading, column length and or diameter, flow rate, column temperature, or few more parameters that may be adjusted. No adjustment is permitted for wavelength. This is important. The wavelength has to be within the acceptance criteria of USP 197U. I hope that the requirements of interpretation of chromatograms is understood well. Read and understand USP chapter 621 fully. Same information may be found in EP 2.2.46 also. Thanks for watching. For more videos, please do subscribe, like and share. Thank you.